Assalamu alaikum students. Today is our online lecture number 3 and today we will study how to find the numerical solution of the nonlinear equations. Today we will study the first basic technique of finding the nonlinear equation, and that is a bisection method. And as the name suggests, that the bisection means divide the interval or divide anything into two equal parts and split that into the from the midpoint. So its definition is that bisection method in the mathematics is a root finding method. So our basic objective is to find the root of the equation or to get the solution of the equation. So the bisection method in mathematics is a root finding method which repeatedly bisects. So we have to use iterations and we have to again and again repeatedly bisect the interval into two equal parts at the midpoint, and then select the subinterval in which the root must lie for further processing. So our main objective is we have to split the intervals and we have to find the root of that nonlinear function or nonlinear equation, and for that we use iterations. Four portions how to find the root. So first we will discuss the root finding problem, and then we introduce what is the bisection method first. So then we apply the bisection method on some specific example, and then we will study the theoretical study and what is the relative error of the bisection method and its stopping criteria of the bisection. Its history is that the root finding techniques or the approximation starts from almost 1700 BCE. That means before Christ era. So it was one of the most demanding technique from the start of this process involves. Now, what is the root of any problem? Like if we have any function, what is basically the root? The root is that if we substitute that value, if for example 2 is the root of any equation, so what we do, we just apply this 2 in that specific function, and then f of 2 is equal to 0. So this process involves finding the root or solution of an equation of the form f of x equals to 0. So that means x is the root of that particular equation. It may be a linear equation, it may be a non-linear equation. So the root of the equation is called the 0 of the function f. So if f of x is 0, or f of r, if r is the specific root, f of r is 0, then r is said to be the 0 of the function f. So what is the bisection technique? Now come to the main objective. The bisection technique is that we have to select some interval, and then we go through the subintervals based on the condition, and the condition I will tell you. So its statement is, suppose f is a continuous function defined on the interval a b. A is the starting point of the domain and b is the ending point of the domain, and all the elements or all the numbers are in between a and b, including the number a and b, with f of a and f of b is of opposite signs. This is the first condition, that if f of a and f of b are of opposite signs, then that means root lies in this interval. If f of a and f of b are of same signs, then root doesn't lie in this interval. So we have to select any other interval that gives opposite signs of the functions. So the intermediate value theorem. Now let me explain the intermediate value theorem. The intermediate value theorem, the statement of this is that if f belongs to C of AB, that means f is a continuous function in the domain AB, and k is any number between f of A and f of B. That means k is any image of that. Then there exists a number C that belongs to AB. So C is the intermediate point in the x-axis, and for which f of C equals to k. So the image of C, small c, after which function applies, so is equal to plus k. So the image of C, small c, is k, and k lies between f of A and f of B. So that is intermediate value theorem. So if we apply here in the bisection technique, and that says that the intermediate value theorem implies that now C is any intermediate point between the x-axis A and B, any point, and the image lies k lies in the y-axis. So here the specific value, the intermediate point C is in the bisection technique is the midpoint. So you have in every iteration, in every step, you have to split the interval into the intermediate point C. So C is always the midpoint of that function, so that interval. So the midpoint, the intermediate value theorem implies that the number P exists. So P here is the reference midpoint in this bisection method. So that number P exists in the interval AB with f of P equals to 0. So P will be the root of that function if f of P equals to 0. So we have to check f of A and f of P in every step is of opposite signs, and we have to select the subinterval based on that opposite sign technique of the function, and then we have to apply the root, and if at that root the function value is exactly equal to 0, then we say that this is the root of the bisection method. Is also known as the binary search method. So binary search, bi means 2, so it split the interval into 2, so that means a binary search method, which is based on the intermediate value theorem. Intermediate value theorem says that the C is any intermediate point. The speciality is that C is the midpoint of that interval. Suppose a continuous function f defined on AB is given with the f of A and f of B of opposite signs. By the IVT intermediate value theorem, there exists a point P that belongs to AB for which f of P equals to 0. It will be assumed that the root in this interval is unique. Yes, bisection method is a great method, although it is a time-consuming method and it involves a number of iterations. But root obtained in that interval is always unique. It cannot be more than one root. Condition is that f of A and f of B are of opposite signs. Now if we split that into midpoint, then we get the two subintervals, first subinterval and the second subinterval. So based on the opposite sign technique, we have to select that whether we have to select a C interval or we have to select C B interval. So C is the midpoint, or we can say P is the midpoint here. Okay, so A, P and P in B based on opposite signs. So subintervals, subintervals and subintervals, and then we get the one unique point that is the root of that function. Okay, although the procedure will work when there is more than one root in the interval AB, we assume for simplicity that the root in this interval is unique. Yes, it is unique. The method calls for a repeated halving. Halving means bisecting of subintervals at each step, locating the half containing. Now P, in every step P will replace either A or B based on the opposite sign condition. So in every iteration the value of either A or B is updated, so your subintervals are also modified. So the computational step is that let P1 equals to A1 plus A1 plus B1 first iteration. Basically so first iteration has the midpoint A1 plus B1 divided by 2, so that is the midpoint. And then if f of P1 is equal to 0, then P is the root, and if not, then P1 will replace either A1 or B1 based on the opposite sign condition. So I hope that you got my point. And it is all about the computational steps, and the algorithm is given. So you can also make algorithm by your own self. Okay, so this is a graph of the bisection method, and graphical representation says that f of A and f of B must be of opposite signs. So AB, although AB is it lies in the first quadrant, second quadrant, it doesn't matter, but f of A and f of B must be of opposite signs, then root lies in this interval. So all of that explains this. And if P is the midpoint and f of P equals to 0, then we stop this stopping criteria. Now we come to the stopping criteria for the algorithm, and that is okay, in every step, one thing I forgot to tell you, that with every question or every equation, tolerance is given. Okay, every calculation of your method should be in radians, not in degrees. So set your calculators in radians, because MATLAB will also calculate in radians. Okay, so stopping criteria must have the tolerance. In every question, tolerance is given. So tolerance means that if, for example, we have to calculate up to 4 decimal places, that means 10 to the power minus 4 tolerance is given by epsilon. So that means that you have to calculate each and every calculation in 4 decimal places, not less than 4 decimal places, not more than 4 decimal places, and in every step you have to round off that. So the stopping criteria is Pn minus 1 divided by Pn is less than less than tolerance. So if this criteria meets, then we say we get the root in this specific interval. Okay, so f of Pn mod is less tolerance. Now we apply the bisection method in this specific question. Now it is a very simple kind of cubic equation, and it says that f of x equals to x cubed plus 4x square minus 10. So polynomial equation, simple equation. Domain is not given. If the interval is not given, then you can also find your interval by your own self by just estimating that if the root lies between 0 and 1. If not, if it doesn't give the opposite signs of the functions, then it means 0, 1 is not doesn't lie in this interval, and then you have to select 1, 2. So in this example, it's given that the root lies in 1, 2. So that means it is between 1 and 2. It may be 1.5. So you have to split between the midpoints. So show that the f of x equals to x cubed plus 4x square minus 10 is equal to 0 has the root in 1, 2, and use the bisection method to determine an approximation to the root that is accurate to at least within 10 to the power minus 4. So that is tolerance. Tolerance is given that you have to do the calculations up to 4 decimal places, correct up to 4 decimal places. So we start this. Our stopping criteria is basically the relative error test. So a relative error test is Pn minus 1. So two consecutive midpoint approximations the difference must divided by the original value must less than tolerance. So I will show you in the example how this stopping criteria means. Step is that we start this our question, our example, and our starting point A is 1 and ending point is 2. So we check that whether the function has the opposite signs or not. So f of 1 is minus 5 and f of 2 is put in after applying these values into the function x cubed plus 4x square minus 10, and the intermediate value theorem says that this is the continuous function, although it's a polynomial function, so that means it is a continuous function. And f of 1 is a negative sign and f of 2 is a plus 14 positive sign, then it is guaranteed that the root lies in this interval. Now we can split it from the midpoint. So the midpoint is between 1 and 2 is 1 plus 2 divided by 2. That means 3 by 2 is 1.5. So that means that f of 1.5. Now check whether f of 1.5 is a positive or negative. Then we select the subinterval based on the opposite sign condition. For the first iteration of the bisection method, we use the fact that at the midpoint 1 to 1.2, f of 1.5 is 2.375. Now f of 1.5 is positive value, so this will update the previous positive values, or this will replace the previous positive values, so that will replace f of 2. Okay, now your B is updated because of the P, because it is a B is a 2 before that and it gives positive value. Now your subinterval is selected, f of 1 equals to minus 5 and f of 1.5 equals to 2.375. So positive sign is updated and the previous positive sign value is finished. Okay, again this is the second iteration, and the intermediate value theorem says that root lies in the interval 1 to 1.5 for the second iteration. Okay, now we again split this 1 to 1.5 subinterval into a further subinterval, and that is 1 plus 1.5, that is 2.5 divided by 2. That means 2.5 divided by 2, that gives a value 1.25, and 1.25 check that whether it is a positive or negative. So we select the subinterval based on the opposite sign technique. So again and again we used one technique, and a very simple technique. So 2.5 divided by 2 is 1.25, and 1.25 if we substitute this in the function, then 1.25 the function value is minus 1.7969. Okay, so up to 4 decimal places. We have to select each and every calculation up to 4 decimal places. So that is why f of 1.25 is the negative value. Now it will replace 1 because f of 1 is -5 and f of 1.5 is 2.375 and f of 1.25 is -1.7969. So that means it will replace or update the value of the negative function value, previous negative function value. That means 1 is now finished, and the a becomes 1.25 and the subinterval is selected between 1.25 and 1.5 because the root lies in this interval due to the opposite signs. Now the midpoint of the 1.25 plus 1.5 is equal to 2.75 and 2.75 divided by 2, that makes it 1.375. Okay, 1.375. 1.375 is the midpoint, and so in this manner continue these all iterations, and the midpoint is again and again determined, and it replaces whether it replaces a and b depending upon the opposite sign condition, and we can write it instead of this theory step by step. We just make a table, and in the table we have to, in the first column we have to represent number of iterations 1, 2, 3, and second column is represented as A, and third column is represented as B, and fourth column is represented as P, which is the midpoint, and f of A n is the next column to show the values of the function at A, and then f of B is the second one as to show the values of f of p, and f of pn is the values at the midpoint. So p is always updated, a and b is always updated because of the midpoint p. So first iteration you can see is this one, and it is we have determined before. So again in this next step is the second iteration, and second iteration is between, like, a is 1 and b is replaced as, instead of 2 we write it as 1.5, and p is 1.25, and again -5 and -1.97969 basically. So relative error is also, relative error is pn minus p and -1 divided by pn should be less than the tolerance. Okay, relative error is step by step calculated. If you don't have any time, then don't use the stopping criteria, just get the root of the equation. If it is asked, then you have to tell what is the relative error test or the stopping criteria of the bisection method. Okay, in the third step is 1.25 and 1.5, third iteration basically. So midpoint is 1.375, and again f of a is -1.7969 if it is a 4 decimal places, and f of p is 0.162. So relative error is also calculated as follows, and continue in this manner. We just use one technique again and again and again, and we reach up to the 13th iteration. And the 13th iteration is solved up to 13 iteration, and I guess it will be solved. You have to do 1 or 2 more iterations to get the specific root of the equation. So the tolerance meets relative error is 0.00004 times 0 and 9. It gives the values, opposite values, as one root of the equation. So we can apply this in MATLAB. Okay, so graphically it is represented by, this equation is represented by this graph, you can see, and also we get the root of the equation. So bisection has very significant drawbacks because it is relatively slow. Its convergence is very slow, although its solution is unique and convergent, but it is very time consuming method, so it needs a number of iterations. It is a relatively slow method, so it's guaranteed that you will get the perfect solution for that equation. So this is all about the bisection method, and I will tell you the many other examples to solve, and one example is you have to try it by your own self, and you have to do the calculations in radians, because that was in this example was a simple polynomial function, so it doesn't matter whether the calculations are degrees or radians. But in the next example I will tell you the function that involves cos and sine and exponential, so that will affect your calculations may vary in the degrees and the radians. So the equation you have to try by your own self is f of x equals to x square minus sine of x minus 0.5, and the tolerance is given up to 4 decimal places, and the interval domain is between 0 and 2. So you have to try it by your own self and get the root, and I will ask you in the next lecture. So this of root finding method. So if you have any questions, any queries, you can ask me, and you have to try it by your own self, and then we will apply it in MATLAB. So thank you so much.